Okay, my friends, stand by. The world's premier genius, Einstein. 5 ways Albert Einstein changed the world. And they go on to describe how, when you say genius, everything pops up Einstein. That's the first thing that pops into your mind is Einstein when you say genius, because he is the premier genius of the world because of his theories of general relativity, special relativity, and so forth. Now, let's examine those theories, because I have different theories. Now, I'm no big shot by any means, but I need to show my theories to see if they hold validity according to Einstein. And I can tell you right now, Einstein and I are not on the same page. This is the page I'm on, is light being able to accelerate, being able to slow down. It's a particle which creates a wave because of its magnetic field. Let's get started. You know, I'm not doing this to run down Einstein. He did what he could with what he had, but I have much more information to work with now than what he had. I can see the particles as I have shown you. These are the particles of light. And I'm going to go into so much detail, I'm sure you're going to be snoozing by the time I'm done. But, you know, he's a genius. I'll give him that. So am I. My Army GT score was right there, 139. All right? Army GT has a long history, runs parallel research. Anyway, if you scored 136 or higher prior to 1980, Mensa will accept the result as proof of being in the 98th percentile. Mine is 139, so I'm 3 points higher than the 136. So I should be able to talk in this realm. I did this my whole life, and I worked in electronics, so I had to fully understand how electronics work, and I do. Okay, my friends, this is going to be about physics and about Einstein and about what his contributions to physics were and about my new atomic model, which replaces the standard model. And I'm going to briefly give you a description of what I have here on the screen. This will take maybe 5 minutes tops, and then you can go about your life, go back to your video games, whatever. But I am going to continue on for an extensive amount of time, going back into my early days, how I started into this, because I have to develop some credibility, which I have plenty of credibility, and I will show it and I will discuss it, and it ain't bragging if it's true, and it's true. So let's get started with what I am claiming these pictures represent, and then we'll go from there. Okay, my friends, today we're going to just have a ramble du jour about Einstein and what his theories were and what his laws, really they became laws, and you had to follow those laws to stay in physics. Which one of those laws I totally disagree with is the speed of light is consistent. It's absolutely not. You can accelerate it, you can slow it down. It's a particle, it's a wave, it's all the things that I have been saying it is, and I can prove that is. I'm not just guessing. Now, Einstein had his theories which were not based on any substantial evidence. There's no evidence. It's just his calculations, his mathematics all worked out. Well, no, they didn't work out, because E equals mc squared is total nonsense, really. E equals mass, yes. Energy is mass, no question whatsoever. C squared, there's no such thing. Light can speed up, it can slow down. C is not a consistent. C is supposed to be an exact speed of light, never changes. Everything that they do in space now with these telescopes and so forth is based on the fact that light never slows down as it comes to us. And that is an absolute wrong assumption. It's just wrong. Light slows down. I can show it slowing down. It slows down in atmosphere, and space is saturated with atmosphere. It's not a vacuum. They know it's not a vacuum, and they cling to these crazy conceptions that they're forced to repeat. Otherwise, they throw them out of science. They get out of here, you're an idiot. You're not saying what Einstein said. Who are you? Get lost. And that's what happens. So you never can change science. You can't change. It never can change to be correct, because right now they can't figure out dark matter. They have no idea how gravity works. They don't even know how heat works. They think heat is just vibration. It's not just vibration. It's additional particles. Heat adds weight. Everybody thinks, oh, no, you heat something up and it goes up in the air. No, only gases. You heat up solid material, it gets heavier. Now, so again, this is going to be a ramble, but I'm going to just start off with, let's just discover, what is light made of? What's light made of? What are protons made of? What is matter made of? And where does it exist? What comes from the sun to us? To make plants grow? To warm up our atmosphere? To give us a suntan? What's coming down at us? Is it nothing? Obviously it's something. What is gravity? How does gravity work? Why do things fall to the ground? It's an electrical magnetic attraction. Everything is a dipole in my theory, dipole electron flood theory, and I will show you we are made of light. All right? Just hold on. Hold on. We, and everything that you see, my coffee cup here, teacup, whatever I'm drinking that particular day, is made of light. So is my glasses. So are my eyeballs. And so are every single thing that you have ever seen is made of light. Because that's all that exists. You ball it up together like a snowball, you got a proton. You make a bigger snowball, you got matter. You got atoms. You get bigger, you got atomic bombs. All right, we did particle acceleration, detection, everything right there. That's what was used. Samsung Galaxy S3 from 2012, a Bosch laser, red pulse construction laser, did all the red ones. And then of course you have the other ones, you know, whatever, just pulse red lasers, you do it. Or green or blue or whatever you got. And that's what this was done with right there. Okay, I'm sure I'm going to get deep into about the argument I had with CERN and everybody, Fermilab specifically. CERN, I asked, is the Large Hadron Collider going to use CMOS? And yes, Large Hadron Collider currently undergoing upgrades to incorporate CMOS technology. That's just exactly what I showed them. Oh, you can't use it, you can't use it. Yes, you do. They had to radiation harden the CMOS so they can use it for detectors, particularly in the high luminosity project, which is a high luminosity. That's what I'm showing them. Allows for more precise measurement, improved particle detection. Key points about CMOS is it's the cat's meow. This is the photons approaching the Venturi and exploding. That is what a photon looks like. It's red and it is slow. That's a green photon, identical shape and form, so forth, only it's much more, it spins much faster. In other words, a red one may spin this speed. A green one is down here. And then the blue is like, and that's the difference, the spin rate. And this one's charging up, just getting ready to flip, because they flip, and they, instead of being a downspin, it flips, and the white will come here, and it'll be an upspin. All right, this is really kind of crazy, because now they're talking about light going this way and that way at the same time. And yes, I can show you that happening. They're Higgs fields. Light is a Higgs field. This is what light is. It's going this way. There's all kinds of other particles of light, but they're not being sucked forward. That's the only reason we're seeing this. And the only reason we're seeing these is because they're concussing with the explosion, which is called the reverse electromotive force. You see way over here, you see those waves going backwards? That's from this nuclear explosion. And it's a sub-nuclear explosion. They see the particles exploding. They're dividing right here, they're rejoining here. Right in the middle, there's nothing but raw energy. Okay, my friends, one of my favorite subjects, Albert Einstein. 5 ways Albert Einstein changed the world. Now, there's Albert right there. Now, he was a German-born physicist. Albert Einstein was so influential. His very name has become synonymous with genius. Here's, oh, I'm no Einstein, you know, that type of thing. While working as a patent clerk in 1905, age of 26, Einstein submitted 4 papers to the German journal, whatever that is, Analysis, that changed humanity's perception of time, gravity, and light. Today, historians mark the year as Einstein's Annus Mirabilis, or miracle year. Yeah, well, miracle, nightmare, whatever you want to call it. Okay, here's continuing on. It says he was just getting started at that age of 26. Today, historians mark the year as his miracle year, and he was just getting started. Now, much of Einstein's work is famously dense. Few people other than physicists need to fully comprehend the mind-bending ideas behind a general theory. It's just not right. You can't understand it. You can't understand it. It's not understandable. And even Yale, if you go to Yale, they'll tell you, we don't know how this works. Just say what we tell you to say and everything will be fine. All right? Few can comprehend it because it just doesn't work. You can make up and, you know, convolute everything to try to make it make sense. It doesn't make sense. And behind a general theory of relativity, light speeds up, slows down. Everybody knows this. Space is not a vacuum. There is no speed of light that's consistent and does not change. And everything they base everything we're doing on is that the light never changes speed. It's ridiculous. All right, see, his discoveries formed a bedrock of technologies the rest of us enjoy every day. You know, we enjoy just doling out money to try to figure out something you can't figure out because you have to go by Einstein's rules. His rules are wrong. Here are 5 ways Einstein ideas changed the world and continue to provide a roadmap for humanity's future. Now, I'm not saying anything bad against Einstein. E equals mc squared, that's fine, but there is no such thing as c or squared c. C is just the speed of light, which goes up, it goes down, it's all kind of difference. They know this. This is nothing more than frequencies at the speed of light. I mean, it's not necessarily that they're the speed of light, but they, trust me, I've shown it a million times. I'm not going to show it again right now. We speed it up, slow it down. Not a problem at all. Now, everybody rests on this theory. Well, okay, my friends, get ready. Einstein, when you think of a genius, Einstein pops into your head. 5 ways Albert Einstein changed the world, and they're making it sound like it's just a fabulous change. Well, I don't necessarily have the same opinion of that change. I say that Einstein wasn't correct. I say light can accelerate, and you can see it. I say light can slow down, you can see that. I say light is a wave, yes, but it is also a particle. And it creates fields everywhere that it travels. When it's quiescent and just sitting around doing nothing, it has its own field. But at that point, there's really no energy to speak of because it's not interacting. Light is only energetic when it reacts. When it sits, it's just sitting around, just waiting to get reactive. Okay, my outstanding friends, prepare yourself for the ramble du jour. Today, I am going to ramble about Einstein. 5 ways Albert Einstein changed the world. And they say, whoa, fabulous, the genius, the most fabulous genius in the world. Anytime you think of genius, you think of Einstein. Now, what did he do? What was the things that he changed the world? How did he change the world? Well, it's related to his theory of general relativity and special relativity and so forth. And I have a different opinion than Einstein. And his theories can't even explain gravity. So I don't see the big excitement about these theories. I say they are not correct. And I will show you why they're not correct, not just because I state they're not correct. I show you they're not correct. Light can speed up light can slow down, light is a wave, and it's also a particle. I show all this stuff. A couple of minutes, you'll be trained. Okay, my friends, again, just a ramble. Well, let's start off with Einstein. Everybody knows who Einstein is. If you hadn't heard his name, I don't know where you live. However, he was known because he went to all these universities and gave lectures and, you know, rose above the others and was accepted as the genius. I have no problem with that. However, I do have a problem with his interpretations of the physics. It's just not right. I mean, that's just all I can say. Light speeds up, it slows down. Light is a particle that creates a big wave because of its magnetic field. I can show and demonstrate all these things, and I have. And I have every bit of credentials as Einstein. It's not bragging if it's true. I was certified as a genius by the United States Army when I was in, and I'm going to show you the test right now. So I have no reason to say that he's any smarter than I am. And I have evidence to show that what I'm showing you is real, not just theoretical. Oh, we got gravity waves and we got this and that. No. Nothing works in the standard model, which is basically his model. They can't understand gravity. Why does sun fall to the floor? I mean, that's just unbelievable. But they don't understand dipole electron flood theory. Without that, you're done. So let's understand what he has to say about general relativity and special relativity and what I have to say. Okay, my friends, before we get started, everybody knows Einstein's a genius. Well, I have some capability on myself. I studied all the same things he studied at a much later date and had much more information than he has. And now I have the light research to prove the things that I was saying back then against Einstein. I said, this isn't right, that's not right, this isn't right. I was against all of them because they had a big, huge positive core in a proton, and there were little tiny electrons floating around them. A proton, one proton is a hydrogen nucleus, one proton, and it has one tiny electron, 2,000 times smaller almost. Same charge, and floating around outside, it would have snapped in just like that, smack. I said, you guys are crazy, this is impossible. Everything you're saying just makes absolutely no sense. He said, doesn't matter, Einstein said it, you're going to say it. I said, like hell I am. And I got out of it. Okay, I took physics basically at every college that offered it. I mean, all over the world. I went to the University of Geneva for particle physics. I didn't go there physically. I went through Coursera online, but I interacted with the professors, and I showed them all our stuff 10 years ago. And it affected how they did business over there at CERN. I don't care what anybody says. We had an argument back and forth, not really an argument. I just said, the things that I'm showing, which are here, hold on. The things that I was showing them, whoops, oh, here, by the way, I got to show you this. This is my Army GT, 139. GT is general technical. Technical, that means you know how things work, you know how electricity works, and motors and gears and pulleys and shafts and cranks and cams and valves and all. You got to understand everything about technical stuff, and at that time I did. And this was me. I was a Spec 5. I got out February. Here it is right here. The Army General Technical has a long history, runs parallel with research, and means for attempting the assessment of intelligence or other abilities. Intelligence means the guy knows the capital of California or something like that. That's not intelligence. That's just you repeating something somebody told you. I know how things work, and I understand biology and chemistry and physics and anatomy, and I understand it right down the line because I studied it, and I'm capable of understanding because I have a 139 GT. And here was what it says: a composite score derived from elements, a composite of everything you can understand. is called General Technical, usually abbreviated GT. If you scored 136, now don't forget I was in 139 or higher, before 1980, Mensa, the big smart people, will accept the result as proof of being in the 98th percentile. So if you're 136 in the 98th percentile, I was 139, that puts me over 100. Now I'm doing this because nobody knows who I am, but in 1970, I serviced nuclear Nike Hercules missiles when I was in the Army up in Alaska. And I did deep into physics and chemistry and everything you could possibly do. And these were the pictures of the light. That's the photon of light. And that's a particle wave. The photon, that little bit here, is inside of here. But it has a big field around it, so as it moves forward, it lights up everything in front of it. Anyway, this was from long ago. The transfer of energy is from light to atomic vapor. Everything is light comes down as atomic vapor. And then I get into gravity and all that stuff. Molecular polarities. I mean, I did as deep as you could get. And my theory was that there's only two types of interelectric forces, dipole-dipole interactions. Some of them are polar, some of them are nonpolar. But yet they have to be dipoles. You can't have one big gigantic positive and a little tiny negative just floating around separated for some reason. They don't do that. They come together. And this is what they could not explain anything. But gravity is the fact that dark matter is incorporated into light. It is the dark side of light. You have bright light, you have the dark side. I'm going to show it to you right now. And the dark side has a mass and a weight to it. The bright side just glows and burns. It doesn't have any mass. It's pushed by the black particle. And the black particle they used to call the carrier boson. I don't know why they went away from that. They keep going here and there, and now they got axions, and who knows what they come up with. Every day there's a new name, and it doesn't mean much of anything, because the only two particles that exist, as I show in my dipole electron flood theory. Hold on. Oh, wait, you got to see this first. I took courses just about everywhere in the world. And this was Professor Shankar down at Yale. It's free. You go free. I took through Coursera. I went everywhere in the world to physics courses. Anyway, this is one, just you can go online, well, he's 48 courses. I mean, it's meaningless because he doesn't understand it. And he admits it. That's why I like this guy. He's good. Listen to what he says. Here's, Professor, this is a very exciting day for me, because he's starting his class. Now listen to what he says.
It's a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now, I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else.
What can I say? And he's right. Nobody understands it. Not a single one of them. They come up with the most nonsensical explanations for things. All you have to do is look at dipole electron flood theory. This is the case. She becomes closed. Okay. This is a very exciting day for me, because I'm going to tell you the actual truth of how this quantum mechanics stuff works. Then you can go back and spread your intelligence everywhere. Ignorance we got too much ignorance now. You got way too much ignorance. We got to inject a little intelligence. And this is a proton. Okay, this would just be me bragging if it wasn't important, because every single thing they do in space is based on light never slowing down. It's impossible. It's just absolutely insane to believe that. And I showed you light speeding up, slowing down, or I will. So this is much more important than just Einstein being wrong, but he was definitely wrong. And if we have to base everything we're doing on his original work and we'll model the whole thing around that because he was the one that figured it all out, no. It's just wasting your time. And you're just calculating all these crazy things. And I told him, I said, you're giving me things to calculate. Just insane. It's just ridiculous things. And just like Professor Shankar said, nobody understands it. They just repeat what they're told to say, and then they're genius. The better you can repeat exactly what you're told to say, the higher your grades are, the more likely you're going to be successful. They're going to give you good grades. Ooh, I earned A's from Yale. Well, that does not work for me at all. I think you were just robotized, menticide. If you don't say what they tell you to say, they fail you. So what are you going to do? You're going to say, no, that's not right. Well, I did. And of course, they tried to fail me, but they didn't. They couldn't. And the actual honest truth fact was, I wanted an A in physics. And my professor said, no, I'm only going to give you a B. I said, no, you're going to give me an A. And we almost came to a fist fight. I'm not kidding you. And I said, I will destroy you in a competition of calculating anything you want to calculate. And I threw out something. I forget. Well, I know what it was. It was a dipole. It was a molecular moment. We had to calculate the dipole molecular moment of a polar molecule, which means where is the center of polarity. About 3 seconds later, it's hard, I'll give you A. So, but nobody else could do that because nobody else, you can't understand it. You can't understand what they're telling you. So anyway, it did not work for me, and I said, you people are all crazy. And they were. They had just nothing but egos, and they just, all they wanted to do was to prove that they were smarter than you. And you know, I got to tell you the honest truth. When I first got out of the Army, I showed up for class. I was a little late because I got out in February. And I went into the class and it was filled. There wasn't a seat available in the class. And I said, oh, well, and I started to walk out. He says, no, sit on the radiator. You'll be all right. I said, I'm not sitting on the radiator all year. He says, I'll tell you what, next week you can pick up any chair you want in this class. And I'm thinking to myself, what the hell is he talking about? And then a week later, there was about 6 people left in the class. He was so arrogant and so nasty that everybody left the class. I'm not kidding. That's an absolute fact. The 2 things I just told you about him saying, don't worry, next week you sit anywhere you want, fact. Him saying, I'm going to give you a B, no A, I forced him to give me an A, fact. All right, and that is, you can't live in academia and fight your way through it unless you really, really, really want to fight. And I'm telling you, you're going to fight like hell, and you're not going to get anywhere. It won't matter. You know, anyway, this has been an ongoing battle with me since I was breathing oxygen. Well, okay, my friends, I decided I better set you up for this. I am just going to do a ramble about Einstein and what his theories were. And in my theory, his theories were not correct, and that's what's kept physics from advancing. I mean, it hasn't advanced in 100 years. And this was Einstein, and his very name has become synonymous with genius, which means if you say he's not right, you're an idiot. So this is what's happened to me, but I am right, and I can prove I'm right. He did the best he could with what he had. He just was wrong. And that's just no question about that. Okay, now these pictures go back to over 10 years ago, about 12 years ago or so. 2013, 2014, right in that area. And these are taken with a cell phone, which uses CMOS, complementary metal oxide silicon detectors. And I reported this to CERN in Geneva, you know, my professors at the University of Geneva when I took a course there. And I said, we're seeing these particles, and they're exactly the same ones that they see at Fermilab, and they said, no, you can't see those because you can't see them with CMOS. CMOS can't handle the energy. And I said, no, it is made to handle electrons, but not made to handle protons. We are in this realm right here. We're using light. They're using these. When these hit our sensor, you're just banging a little pop, pop, pop. These hit, and when they break, they can send off chunks like this, and it just smashes the detector. So they're right. They had to radiation harden them. But this is what I talked to them about, and they are doing that. And they have done it already, I believe. But this was from 2013, 2014, right after 2014, I would say. And I went to took the course at University of Geneva. I think it was 2015. Because I got no response from Fermilab. And these were the particles, identical, same particles. Hold on one second. Let me show you what I sent to Fermilab. And they have me blocked. I can't comment anymore. So anyway, this is what I saw in, I think it was 2013, these particles. And we had seen them using a light. This is from Fermilab showing the particles. Don Lincoln, and I contacted him. I said, Don, we found the particles, the same thing you found, only we use light instead of protons. And boy, it did not go well at all. We are not, well, he blocked me. Now, I know, that's it, there it is. That's the particles. Only they just see them in a big mess. Because they started with a big blob like this, and when they thought it was a solid piece, it isn't. When these things hit head on, they just go splash like this. And here's what I'm showing you. This is what we started with. That's our light particle, and it consists of those two. And when we hit it into the Venturi, it did separate. It actually, that's called fission. When there's a black one left, a white one, that's fission. It came back together here. They fused back together. Somebody said, oh, no, fusion, you have to use protons. No, you don't. You don't have to make elements with it. You just have to assemble particles is fusion. If I fuse this to that, I don't care what it is. So this is fusion, that's fission, this is raw electricity. And this is acceleration of light. Einstein just wasn't right. This is the backflow. It's called reverse EMF, reverse electromotive force. It's coming backwards. They just had a big thing, oh, we found light can travel backwards and forwards at the same time. No, it's bouncing backwards. I'm telling you, it's just incredible that they missed all this stuff. And that's the particles. And this is coming through the air, banging into these particles. It's going to get bigger, 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 and it's going to go flip. And that one's going to come in the front and start to accept. That's a downspin. This will be an upspin. And they polarize themselves to the Earth. All of this stuff I've shown. And here's what Fermilab and CERN do. They take these particles and they smash these big monsters together. Boom! And what happens? This they call a particle zoo. And yes, it is. They've seen all these little bits and pieces and chunks, and they say it can't be used, CMOS, because it's too vulnerable to these chunks. And they're right. So what they had to do was harden it, and they did. And this was after I told them, and we had a big argument about this, and so did I with Don Lincoln. And then he called me a disgrace to science and an embarrassment and all this stuff, and how could you even possibly think of this? And I said, I'm seeing your particles, my friend. And then, boy, it went downhill, and I mean downhill. And so for him to be spending billions and billions of our dollars and to refuse to look at that, that's a national disgrace. I'm sorry to do this, but I can't help myself. It's true. All right, it was right here. I asked ChatGPT, does the LHC, the Large Hadron Collider at CERN, now use CMOS detectors to view the collisions? After a huge argument, yes, now they do. Yes, the Large Hadron Collider is incorporating CMOS. Yes, this is response 1, response 2. It's a prototype. They want to know which one you prefer. Now, so yes, they're using they're trying to. They're developing it right now. Transition to CMOS detectors. They're transitioning. They had to build them. They had to build radiation hardness. I said, you've got to make them radiation hard. I told them all this stuff. All right, cost and proficiency. It's cheap. In summary, while the LHC currently employs hybrid pixel detectors, there is a clear trajectory towards adopting CMOS-based detectors in future upgrades to enhance performance and efficiency in observing particle collisions. That's what we did. Only using a cell phone for a couple of $100. It was a Galaxy S3. It came out in 2012, and Rod Warren started taking pictures, playing around with the double slit experiment. And when I saw all the things he was doing, I realized he was creating Venturi. All right, so then that's when I got a hold of all these people, every one of them. Everyone that was doing this, and I got only responses that were negative. And although by the time I left discussions with the University of Geneva, they said, I said, can we work on this thing together? I mean, here it is right here. And they said, no, we'll follow you on Facebook. I'm not kidding you. That was the response I got. I said, oh my God. So that's just, what it is true. So now they're going to adopt the CMOS, which I was talking about. And that's what the pictures we have from 2012. And I just was assaulted by everybody for bringing this up. All right, just to follow this up so you fully understand this. This at the LHC, they had to set up the CMOS, advanced CMOS pixel sensors with radiation hardness. They had to stop these big chunks from hitting it. We started with light, so we never encountered that issue. It says in summary, the current LHC detector, well, anyway, I think I showed you that before. But they want to increase the CMOS-based detectors in future upgrades to enhance performance. Now, I put in, does a Galaxy S3 Samsung phone use CMOS technology, and when was it released? Yes. The Samsung Galaxy S3 uses CMOS technology in its camera sensor, which is a standard in most smartphone cameras. Everybody's got them now. It's not like CERN is any big deal. They should just buy a couple of cameras and put it in there, except they got to put some filters in before it hits the cameras. I mean, CMOS sensors are efficient for capturing high-quality images. CMOS sensors are efficient for capturing high-quality images, consuming less images while consuming relatively low power. It's a little cell phone, making them ideal for mobile devices. It was released in May 2012. That's when Rod first got this, because these were pretty new. These cameras were considered advanced, leveraging CMOS technology for improved efficiency and image processing. And when Rod got this, he just started banging away at it. And then when I saw it, I said, whoa, this proves my dipole electron flood theory. I got a hold of him, and he worked with me probably until 2020, probably almost. It was a long time we worked together. I got more pictures than you can possibly imagine of light. And I see every single detail in it now, and I know it 100%. Light and I are one, just as you are one with light, my friends. You see this? This is a video I did in 2015. It was called Light is Dark Energy While Traveling from the Sun to the Earth. It's energy, but it's dark because it's not interacting with anything. But they pop in and out. They hit things. But it is primarily dark until it hits anything. Light is just dark energy until it hits something, then it becomes glowing. And I have light is dark energy and matter in the vacuum of space. There is no vacuum of space, but for them, they call it a vacuum, so I threw it in there, a vacuum of space, where light just goes through there. However, it doesn't. It hits and it bounces and it slows down. So we're just being befuddled by this space telescope. It's not doing the job it's supposed to be doing because light slows down. And I show that light slows down very, very easy. I show it all the time. Here's light actually slowing down. They say, oh, well, that's because it's in the air. Well, okay. It's coming in real fast and slowing down. But it was accelerated. And now it's just slowing down. And you can accelerate light? Yes, you can. Here's before it accelerates. It's just starting to accelerate. And this is pulsed red laser. Every one of these has a particle in that wave that's trying to pierce whatever's in front of it. And this is the leading tip of the piercing. And what it's doing is it's exciting everybody else out here, because this baby's got a field in it that's not tiny, it's this big. And it's got to get everybody out of the way. That's the field. So it's a particle-wave duality. And where is the particle, Roger? Well, it's right there. Well, I don't see any particle. Well, how about that? You see a particle now? There's that particle. That's what's in these waves. And this is where it hits. And here is the reverse concussion, forcing these to display as photons. I'm into this pretty deep. Here they're not energized enough that they hit anything to become photons. The only way they become photons is really when they hit against a wall. They think they just hit a wall because the energy's coming backwards at them. This is just the whole thing about we can see light traveling backwards and forwards at the same time. No, it's bouncing. What they're seeing is this right here. That's a bounce. The light is accelerating. We can see it. Normally you wouldn't see this. You'd have to have some very special equipment. This is going through a Venturi, accelerating. Very totally understood principle. And this is bouncing back and going forward at the same time. So yes, they see it, but it doesn't mean much. It's just a bounce. But you can obviously see light accelerates. Einstein was just wrong, and we got to get away from these rules. And no, Einstein, he changed the world. Yes, he did, but I don't think it was for the type of, it didn't work out too good. Let me put it that way. And these are particles. That's the particle right there. That's a photon. It came through as light, but we can separate those as you just saw. Right here, we separated the hell out of them. They came through like this, and when they hit the Venturi, right here, and what does mean? Well, means this right here. The muon, which is the black ball, came away from an electron neutrino, which is a white ball, and the white ball went into a shower, and the black ball went into a sterile muon. That's fission, that's fusion, that's raw electricity. This right here has no weight whatsoever, none, zero, zero. What you want to do with this is put it in a battery or run it through wires to do work. You don't want the black, you want the white part, and that's what we got. It's separated all by itself. We didn't have to do anything. Normally, to rip that white away from that black, it takes literally tons of power. This is the strong nuclear force. These are nuclear particles. It takes a ton of these little particles to make up the nucleus of an atom. So they are nuclear. They're inside. All right, and these little particles have to build up to a certain point, and then they become stable. That's hydrogen, first zone of stability. And then a little more, you get a little bigger and bigger and bigger and bigger. And for some reason, they come in these little periodic chunks. It's like a bigger snowball. You have a snowball this size, it's perfect. It won't fall apart. You got another snowball this size, it's solid again. It's like Russian dolls all the way up the line until you get some really heavy stuff. And all that is dipole flood. And here it is, the nucleus gets bigger and bigger right here. That's all. And the dark still is, in my mind, every one of these atoms, the core is the dark matter. And then surrounding it is the particles that are the white matter. So if you cut this in half, you'd see that black right in the center of this. And if this exploded like in a nuclear bomb, all of the particles that have no weight whatsoever but have the energy would go first, and then the black would follow it, as you will see right now. Okay, my friends, you're asking for proof of how I can say that the white matter surrounds the black matter, and that the white matter is only pushed. It does not have any mass of its own. It has to be pushed. How can I prove that? Right here. This is Teapot Apple II atomic bomb effects. I have it run in extremely slow motion, no sound, and this goes back 10 years ago. And watch what this does when it hits this house. I got to run it extremely slow, and I'm going to stop it as we go forward. All right, so they have a test house, and they got back here, they're boom, and they got a hardened enclosure looking away from the bomb so they can see what's going to happen. And what you are going to see is the just brilliant white, nothing but white, but it doesn't push anything. Everything just lights up, but nothing gets pushed. And it just starts to vaporize and burn everything. Now watch. All right, I'm going to open this up. Don't forget, it's atom central. I've played this a zillion times. And I've watched it, and I understand every little detail of it. And I'll explain every little detail as we go along. All right, so they're going to go pop, boom, stopped it. The atomic bomb has just gone off. And let's say it's a half a mile away. That's what you see. Now, what is going to happen? You should see that thing go flying, right? You would expect the whole house to go flying. Well, guess what? That's not what happens. All right, I'm playing it now. Look, it just starts burning. Nothing moving. Look, now, take your time. Think about what you see. The light is heading this way, hitting face on. The poles are burning. The wires are just smoking. The roof is going to smoke, the whole facade, everything that is combustible. What does combustible mean? It can absorb electrons easily, all right, which are these things here. Now, they will absorb them. Normally, it's just like heat. Everything warms up, it cools down. Warms up, cools down. Well, why is that? What's warming up and cooling down? Warming up is accepting the white particles. All right, do you understand? Warm is putting more white particles into something. We're putting so many white particles into here right now, they can't accept it. There's just so many of them in there, but they're not going anywhere. I cannot explain it. I just cannot explain. There's no mass. I can't explain it. I'm sorry. I have no explanation for that whatsoever. I have racked my brain. The only thing I can think is that they're like a balloon, a really thin-skinned balloon, because they got to have some mass, and apparently they do have some miney mass, but they have to have, I believe, but I'm having a hard time finding it. But all I can say is the proton the muon never changes size. That's it. Never going to go bigger, smaller. It has no energy to it. It doesn't emit any heat whatsoever. It doesn't emit light. Light is heat. So it doesn't emit any of that stuff. It doesn't absorb any of that stuff. All it does is attract the white to crust around it, to become, it captures the white. Everything surrounds it. That's what gravity is. A bunch of dark particles and white particles surrounding it, which is us and the rest of the world, surrounding the Earth, which it's got to have a very lot of extra dark matter, because everything is gravity, gets pulled to the Earth pretty strongly. So there's got to be a lot of dark matter in here that really wants that white to be pulled. That's what gravity is. If you took this right here, let's say it weighs an ounce. If you took that and put it up on the moon, it might weigh a quarter of an ounce. Because the gravity's not the same. Gravity is what gives you weight. If you put this on Jupiter, it weighs 50 pounds. Jupiter's gigantic. It's going to pull it down. That's why they say they're gas giants. They're not gas giants. All that is all the gases are so pulled down towards the solid planet that they form a dense cloud, because they're so compacted. Well, here ours is just floating around. But you get up to the gas giants. They're not gas giants. They're giants, but they're not gas. They're gas compressed on the outside. So let's get back to this. It popped, and we saw nothing but brilliant white. Now what we're seeing is the black is back here, pushing the white. All right, now watch what happens. It keeps pushing the white. It keeps burning. Nothing went anywhere. Look, the house is just roasting. The wires are roasting. Nothing is going anywhere. Now watch what happens. The black catches up. But that's just, no, there it is right there. The black just caught up, and boom, there it goes. That's a nuclear bomb. Once again, these are just light. But it does exactly the same thing as a nuclear bomb, because that's what it's sending out, is light. It sent out all of that white particles out here ahead of the black particles. The house was here. This stuff doesn't have any mass. The house just goes, burns up, burns up, burns up. All of a sudden this comes, gone. This is literally, and I'm not kidding you, I know it sounds insane, but this is literally a subatomic nuclear explosion. All right, take your time. Nuclear, these particles are nuclear particles. They exploded, they broke apart. There they are. They've exploded. They're going to come back together. This will join together with that at a certain distance, and they will create Higgs fields. All right, at a certain distance, it will create the Higgs fields. Wait a second, I don't have any showing up here. Hold on a second. Okay, I know it's insane to say that we upended CERN and everybody else in the entire world in physics, but it is true. They hitting these things together, splashing a bunch of debris everywhere. They have no clue what they're looking at. Here's what happened. What they see is this. This is from Fermilab. This is the Higgs fields from Fermilab. And they see the blue ones and the really high energy ones going and not coming back. I agree with that. They see the red surrounding it and not leaving completely. Some of them do, but a lot of them stay close because they're not energetic. These are the ones that are so close to the nucleus, when they take off, you have to really rip them, and they're gone. And that's what they see. Well, guess what we see when we see our Higgs fields? We start out by sending light, which is actually a Higgs field by itself. It looks exactly like a Higgs field, going that way. You see them? And these are only lit up because of the reverse electromotive force. And this is where you see the light go in both directions at the same time. Well, yes. Doesn't mean, they say negative time. It has nothing to do with time. The particles go backwards. Some of them go backwards. They bounce. Simple as that. Some go this way, some go bounce. So this is what we're seeing is light accelerating. Light is the particle. Light splits. It bounces both directions. The dark matter leaves the white matter because it can't get through the Venturi. And right there, we should be able to harvest it and get free energy. I would say this is all you want, as I showed you in a nuclear bomb, but it has no mass. It just filters right down into a battery or whatever you want, go right through your house, and it wants to catch up with these black ones. So wherever you have a ground, it will seek that ground. And normally, lightning, right to ground, because our ground is dark matter. It's heavily infused with dark matter. But it's got a lot of heat in it too, which is white matter. Heat is white matter. Anything above absolute zero is heat, which requires electrons. And that's why when you get to absolute zero, it's superconductive. Why? Because there's no electrons. It wants them. They go through and instantly they start to create resistance. And then those electrons go, and they start slowing down. Now you have no more superconductivity. The only way you can keep a superconductor is to just suck all the extra electrons out, and that just takes more energy than putting it through a copper wire. The superconductivity is not going to work. The better you get in the metals, yes, and so whatever it takes to make that electron glide through there easy. Whatever you can do to resist, to reduce resistance, yes, absolutely. But you're never going to have a as soon as you push electrons in, they're going to try to fight back because you're pushing them into something, like a motor or whatnot. All right, that's resistance. But if you have enough pushing, they'll run that motor to get to that black. They will go right through you, lightning, static, anything, right to ground. It'll explode you to get right through you to get to ground. That's what electrocution is. And you come right from the lightning that's in the air because it's just a whole ton of these extra white particles. They're not the black particles with them. They're the white particles. Right into the ground. Same thing with static. You collected on you a bunch of extra white ones. And you come up and touch a water pipe, right to ground. You see a little spark go. It's because it's pushing everybody else out of the way. It wants to, just like this. I know I'm going to drag this thing out, but it needs to be dragged out, and we need to understand what we're doing. We don't understand what we're doing now. That's why Einstein, it's my way of thinking, Einstein didn't help things a lot. becoming this icon that you can't do better than him. No, it's just not true. It's just wrong. He's got to get out of the way and make room for the reality of the thing. Now look at this. This is from another one of these. I don't know where this came from, gravity, but it's anyways gravity waves. And you see the white one, you see the dark one. They understand these things are going on. They know they're entangled and so forth. They just don't. We did it with a cell phone. Once again, a cell phone. This was Dylan. This is Rod's nephew. Where did Dylan go? Here it is. Look at this. This is what's on. It was a cell phone. And he's got all kinds of the Pleiades and all kinds of things.
Just last month, I found out you can get your...
I don't know what that was. Something just started talking to me. This electronic stuff is crazy. Look at that. It's all dipoles. Every black and white is a dipole. Black and white, there's everywhere. And all of these are fields. And whatever he had in that cell phone, he came out with this. Now, this was a few years ago. He had just gotten a brand new cell phone. He said, what do you think? And I said, wow. And he sent me a bunch of other ones, too. And then Dylan went dark on me. I don't know. Dylan is Rod Warren's nephew, and they were both sort of helping me here. And I don't know what happened. But, you know, I can understand people want to go on their own and just stay away from this because it's a tough place to be. I'm going to tell you right now. I don't know what to say. Oh, boy. All right, this is another cell phone picture. All right, and where did it come from? It came from New Zealand. It was from Dylan, who was Rod's nephew. And this is what they show from the people that are spending billions of dollars. This is what we get. And here's what we get for free. All right, and here's what you get for free here. Light acceleration, fission, fusion, raw energy. But it's not allowed because they just won't allow it to be spoken about. And they know now that I'm right about the things I've been saying. I think I showed you the stuff about the LHC adopting the same technology we're using right here. They should just adopt it for going out in space. What they're doing in space is crazy. It's absolutely insane. They say that light will not slow down going through all this stuff and all the dust and all the light particles are in space. No, that's totally incorrect. It is slowing down as it comes to us. It's not redshifting because the galaxy is expanding. And they have every single thing, 100%, 100%, not 99.9, 100% wrong about the distances in space. They're going through things that are dense. They're going through things that are, not a whole lot. Light slow down more going through the dense than it will here. So they don't know where they are. It's just, we're totally lost in space. Okay, like I said, this is going to run a long time, so I'm just going to give you a real quick shot. Light accelerates. Very easy to accelerate light using a Venturi. Light goes both directions, which they've just been talking about. And we saw light go backwards. It means we can go backwards in time. No, I will explain this. Light through glass, blue, very powerful. These are photons, just as these are photons in the red, identical photons, only the spin rate is different. Because light spins, it doesn't flap like a wave. And these are the green, these are the red, and this is what a particle wave duality is, because the particle is in each one of these pulses. It's a pulsed red laser. So the particle is here, and its field surrounds it, and everything has to give out of the way. So that's why these are all glowing here. Now, this shows you the speed and the particle impact. The green is right above the red, same Venturi. Two pins sticking straight up. The light's going one up here and one down there. And the red is low and it just knocks it out of the way. The green takes off and reconcusses way out here. These are barrel rolling. They're not supposed to do that. They always spin according to the polarity towards the Earth. It's completely polar particles. But these are barrel rolling because they just push them around and spin them around. So these maintain their photon, glued together particles. But instead of spinning like this, They now are spinning like a barrel roll. All right, I claimed light spins. This is exactly what it does right here, just like that. That's what light does, it spins. And all of these white particles that are coming through are very high energy. They keep each other apart. They create all these, what they call interference patterns. They're not interference patterns. You stay your side, I'll stay my side. They're fields that will not let each other touch. And they create these stripes. And what we have here is, that's like the double slit experiment, only this is a single slit. It's just spinning through. The light is just spinning through, cutting around and around and around. Now, we also have this right here, where the light comes through here, and it's just, there's a raw, empty space here. There's nothing, you can't see anything. And then all of a sudden, right here, boom. So what we're going to be looking at next is facing this direction, looking into the light, and we're going to see all these Higgs fields start to show up around the edges. All right, let's see if we can find that. Now, this is what I'd like to see tried, to harvest this white energy here, just like what I'm showing here. Now watch, this is just a laser, very simple laser, takes very little power, and this, if it's white raw energy, which they claim, electron showers are in the high billion electron volts, up to trillions of electron volts, and it's not going to take more than millions of electron volts to get this thing going. So let's say we start with millions, and we can pump it up. See, low energy, high energy. This is from LHC, and these are the muons. They keep back, so they start in coming through this Venturi here with very, very low energy, and then they come up to high energy showers, which create the, exactly what I showed. Now, we could put thousands and thousands of those in a little container like that, a little lunchbox. You carry that around, have portable power. Plug anything you want, anywhere you want, anywhere in the world. AC, DC, 50 cycles, 60 cycles, 110, 220, USB, yada, yada, yada. Whatever you want, if this thing can create additional energy. And they say electron showers raises the energy level to, well, high energy showers. Energy. Low energy. Energy. We started off here low. We came out here high. If we can get this energy before it comes back and put it down to use it, we're golden. Rod Warren and I pioneered the use of CMOS in watching for photons, and now CERN, after I went to University of Geneva and I spoke to them about this, that we used CMOS, they said it couldn't be done. Same thing Fermi Lab saying, because you're going to destroy the CMOS. No, we use light. What they have to do is harden it, and they did, and I will explain all that stuff. They actually shut down and refurbished CERN. For a couple of years it took them to put in these detectors so they could see this stuff. I'll explain it to you. It's all on the internet if you do a little research. And my whole theory is right here. That's everything. That's everything. Now, that's done. You should be trained enough. Muons are dark matter. Their mass is this, and that's one proton, 1839 muons. They're carrier bosons. They carry the white particle. They're cold. They have no heat whatsoever. They don't emit. They don't absorb. They don't reflect. Gravity attracts electrons. They're gravity. They're gravity. They attract everything with electrons, and everything has electrons. They're fixed. They're one size. They never get big. They never get small. That's the same size every single time. They're solid, and their mass is approximately 0.005435 atomic mass units. That's on Earth, the gravity here. Anywhere else, it's going to be heavier or lighter. And they're elementary particles. Electrons are the glowy parts around the outside. These are the ones in the center. They are slow, medium, and fast. They get tiny, they get big. They get tiny, they get big. Tiny, big, doesn't matter. If they're hitting something, they get bigger and bigger and bigger. Harder they hit, the bigger, bigger, bigger they get. More and more and more energy. That's what energy is mass, is how hard you hit something. Energy only. There's no push, no weight. I showed you the house, well, I will. A house just burns up, doesn't move. Mass is approximately zero, but it could go 1 atomic mass units possibly. It's heat. This is heat. And it's also, when it goes fast, it's light. All electrons excite only as they are pushed by muons. They sit around and just don't do anything. They are heat until they're pushed by a muon, and then they become sound or light or whatever. They're not solid. They grow fields as they get pushed. They get bigger and bigger and bigger. And the harder they hit, the worse the field. Look up Casimir effect. Now, that's it. You're done. You're trained. I'm going to go into deep. I'm going to talk about my background. I'm going to talk about why this is so wrong. Physics is out of control wrong. And the only way you can get back in control is dipole electron flood theory. They found the same particles we found. We found their particles. They won't discuss this because we use light, saves a ton of money, and we're paying for this. Billions of dollars wasted. I'm telling you right now, you see what I show you, and if you think I'm wrong, I want to know why. All right? Stay tuned. This is going to get very deep. I'm going to explain why this is just a waste of money and time, all this Webb telescope. Light slows down. It's very, very, very obvious that it's not going the same speed continuously. I'm going to show you Higgs fields that you won't hardly believe. And this is, they can see light going both directions. All right, this is light coming in, but it's also going backwards. All right, and this is light coming out this way. We're looking into that Venturi, and there's nothing but whiteness here. There's nothing. We can't see anything at all. You see these little white spritzes, that's all, but no fields. And all of a sudden, the fields start showing up all around the outside. And about out here, we got nothing but fields. See what I'm saying? Now, this is light accelerating. Nobody can put it in. Light is going back this way. I showed, well, I'm going to show you all this stuff in great detail. So by this time, you might as well forget it. If you're not interested, Vios con Dios. If you are, I am going to show you what the real reality of the situation we're in, what protons consists of, and muons and electron neutrinos, and the whole shoot mess, top to bottom. We're going to go through it. So hopefully that didn't take up too much of your time. Stay tuned, because I'm just going to keep rolling down the road here. It's going to be a ramble, and I'm going to give you a lot of details about my background in this too, why I should be able to talk about this. And we might even be able to get free energy. I don't know if I showed you this yet, but I don't see any reason we can't get free energy. Maybe, maybe not. They came in low energy. They hit over here at high energy. If we can get them before they just get wasted, we use that high energy. It doesn't make much sense not to.